This is the final presentation for Group 707G. This project involves creating a design for a microreactor that can indicate elements found in living organisms and fit on board the current design that the Queen's Space Engineering team has developed for a rover. This needs to be done through chemical indicators displaying a visible change. Once testing is complete, the sample must remain on the rover and not contaminate the other samples in the reactor, as this microreactor must perform 3 consecutive tests. Some key problems encountered during this project are as follows: which chemicals to use in order to indicate through soil samples if the environment is capable of supporting extinct, extant, or no life, and also how to reduce contamination and chemical spills, more specifically including how to effectively put a lid on the tested samples and how to minimize the amount of sample residue in the sieve and tubing.
The design process. So the design solutions that were created by the team were based off of the main functional requirements and constraints that were given. So the main functional requirements were that the microreactor must indicate life in 3 consecutive samples. It must have an adequate waste storage system and a sample storage that must be sealed to reduce the possibility of sample contamination. The main constraints of the microreactor is that it must be less than 5 kilograms, it must be less than 30 by 30 by 30 centimeters, and the cost must be under $90. The 3 proposed design solutions that the team created were the forestation design, the motorized churning design, and the simple design. These 3 solutions were compared in a weighted evaluation matrix that were based off of certain criteria, such as cost, contamination in the sample collection, waste management, minimized use of motors and electrical components, and a few others. Overall, the simple design had the highest score, so it is the design solution that our team chose.
Okay, so I'm going to be talking about some of the technical, environmental, and financial factors. The team tried its best to meet all the client's technical constraints while still being mindful of the environmental impacts of the design. These technical constraints included things like size, weight, speed of analysis, and the budget. As a result, the design of the reactor was a constant exchange between being able to meet all these requirements and yet still have a design that was as environmentally friendly as possible. For example, ABS plastic was used for the reactor frame because of its strength and affordability. However, the option of a more environmentally friendly plastic existed, such as polylactic acid, or PLA, which is biodegradable but would cost more to manufacture. Realizing the client had a restricted budget of $90, using this plastic would strain the budget more. The team came to the executive decision to use ABS plastic instead. There were plenty of examples like these throughout the design and decision-making period, but the team believed the perfect balance between the client's constraints and the demand for a more environmentally friendly design was found. Next slide, please. In all the decisions made, the client's interests were always in the best mind. What would work and what could be cumbersome in the setting of the University Rover Challenge. As such, and as was previously mentioned, the team came to a design solution that highlighted the efficacy of a simple design, one that would be less likely to fail due to convoluted technical issues during any field testing the design would theoretically undergo. This is just a glimpse into some of the technical, environmental, and social and financial factors that the team wrestled with during the design process of the microreactor.
The design solution. The design functions as follows. There are 3 funnels at the top of the microreactor, all connected via a tube to 3 separate containers. Each soil sample is loaded into its respective funnel. There is a sieve at the base of each funnel, which is used to achieve the desired soil sample size. The samples pass through the sieves and fall down a tube into the respective containers. There are 3 canisters that contain Burette protein test chemicals. The Burette reagent is a solution of sodium hydroxide, hydrated copper sulfate, and potassium sodium tartrate, and it is mixed with water in each of the 3 cylindrical canisters. The solution then flows through a pipe into its respective testing container to react with the soil. The solution is inherently blue, but when the cupric ions react with the nitrogen atoms present in peptide bonds in amino acids, the solution turns into a bright pink or violet color, indicating a positive test for life. The canisters in the solution is connected via a thin pipe to the 3 different containers. Once the soil has made it inside these containers, the solution is transported through the thin pipes, turning the soil into a slurry and allowing the chemical protein test to take place. The containers are made out of glass, allowing a Raspberry Pi camera to detect any change in color.
Throughout the semester, the client outlined many functional requirements and restrictions to indicate an effective design for the microreactor. Things such as volume, time for testing, waste management, testing capability, weight, and budget are all highly important factors in the effectiveness and success of our model. The evaluation for a design is based on these markers for success to provide an image of how well the model fits into the client's wants and needs. First of all, the design respects the client's $90 budget and comes out to around $70.56. The design was also completed within the 12-week timeframe. The entire microreactor is less than 30 by 30 by 30 centimeters in dimensions and weighs less than the 5 kilo limit. The chemical tests are able to provide results in 5 minutes, and all waste is kept in individual testing containers to prevent contamination in the system. The containers are all sealed and are all clear to be able to display visual changes within the containers. The design fulfills the needs of the client and respects the limitations set out.
One recommendation to enhance the design would be to add a lid to each of the 3 entry points of the microreactor. An example of this would be to implement a lidding mechanism using a Raspberry Pi. Doing so would eliminate the possibility of a spill if the rover were to find itself at an extreme angle, which the current design is susceptible to. To further improve the design, a stirring system could be implemented in each of the 3 containers. Although this would increase the complexity and cost of the model, it would improve the sample slurry making process, which is a key component to the success of the microreactor for this project.
Delivery and disposal. Due to the COVID-19 pandemic, delivery of this design is strictly computer-oriented. With rolling lockdowns, the team would not be able to collaborate to construct an actual model for the client. With this in mind, the design in SolidWorks provides a good representation of the microreactor. This would allow for good implementation of the design if the client sees fit. Finally, without any construction of the model, there is no need for disposal. However, if the design was to be implemented, most of the internal components could be recycled or reused as they are plastic or containers and have multi-purpose uses. Thank you.